All right, so on Tuesday we started a new chapter, which is channel coding. And the basic idea of channel coding is to add structured redundancy, and by using which we can protect the information from distortion. So that's the basic idea of channel coding, just to add redundancy, and those redundant information can be used to protect the information from distortion. And a very simple example of coding would be parity check. We just add a parity bit for all the bits, right? And by checking the parity bit, we will know if there are some errors happening in the transmitted information. So that's coding. And also we talked about the two different types of error control. And one is called error detection and retransmission. So in this case, we only need to use relatively simple coding schemes. And for these coding schemes, the only objective is to detect whether there is error or not. The coding does not need to necessarily be able to correct the error, right? So the only requirement that we have this coding for the first scheme is to detect the presence of the error. And in this case, if the error is detected at the receiver, and then the receiver can send back a negative acknowledgement to the transmitter, such that the transmitter can do a retransmission. And this is kind of like a closed loop control. So there's a forward link, and also there is a backward link from the receiver to the transmitter. Okay? And the second type of error control is forward error correction. So for forward error correction, we no longer need a reverse channel from the receiver to the transmitter. Instead, the coding needs to be sophisticated enough such that the receiver can not only detect the presence of the error, and the channel code should also be able to correct the errors. Okay, so this is called a forward error correction, FEC. Okay, and in practical communication systems, these two different types of error control schemes are usually used together. Right? At the lower level, we use forward error correction, and we try to correct as many bits of errors as we can. And then on top of that, usually we have the error detection and retransmission. Okay, and so in this case, for the forward error correction, we will need a lot more complicated coding scheme compared to the error detection coding schemes used in the upper layers. Okay, and in many of the practical communication systems, for that error detection and retransmission, we use a coding which is called cyclic redundancy check. Okay, CRC code. And in the lower level, for the forward error detection correction, and that's the code that we are going to discuss in this chapter, we can use linear block code, we can use convolutional code. We are using turbo code in the 4th generation cell phone systems, and we are going to use LTPC code for the next generation of cell phone systems. Okay, and this code, they are sophisticated enough such that they will allow us to not only detect the presence of the error, but also correct those errors if there is any. Okay, so for the error detection and retransmission, the scheme is usually called automatic retransmission query. Okay, automatic retransmission query, or ARQ. And we looked at 3 different types of ARQ schemes, which are stop and wait, continuous ARQ with pullback, and continuous ARQ with selective repeat. And also on Tuesday's class, I mentioned there are more advanced ARQ schemes. For example, we can have hybrid ARQ. Okay, and also we can have incremental redundancy ARQ. And then we moved on to the introduction of structured sequence. All right, as I have mentioned, the basic idea of channel coding is to add structured redundancy such that we can use this structured redundancy to protect the information from distortion. And this structured redundancy depends on the structure of the sequence itself. Okay, so we looked at 2 very simple examples of error detection and error correction by using repetition code as an example. Repetition code is essentially the simplest form of coding schemes, and in reality, not many people are actually using repetition code because it's kind of inefficient, right? We need to repeat the information over and over again such that to achieve the objective of error detection or error correction. And as a very simple example, so if we repeat the information twice, okay, instead of transmitting a 0, we transmit 0 and 0. Instead of transmitting a 1, we transmit a 1 and a 1. So this is a twice repetition code. And this code is good enough for us to detect if there is a 1-bit error, right? So, for example, if we transmit a 1-1, however, at the receiver we receive a 0-1, so at the receiver we will know immediately something is wrong, because the receiver can only is expecting to receive only a 0-0 or 1-1. If it receives a 0-1 or 1-0, means something is wrong, but the receiver does not know which bit is wrong. So in this case, it's good enough for error detection. And another simple example is we repeat the information 3 times instead of twice, right? So instead of transmitting 1, we transmit a 1-1-1. Okay. So in this case, the valid code words at the receiver will be 0-0-0 or 1-1-1. These are the only 2 possibilities. Anything else means there is an error there. Okay. So for example, if we receive a 0-1-1, and actually the receiver can guess that a 1 has been transmitted because there are more 1s than 0s. And this is called a majority decision rule, right? We look at the majority, and if the most of them are 1 and only a few of them are 0, we make a decision in favor of 1. Okay? And actually, the majority decision rule is exactly the maximum likelihood decision rule, and it can minimize the error probability. Right? So the decoding for this repetition code is actually quite simple. We just say, do we have more 1s or do we have more 0s? So in this case, it does not only have the error detection capability, it also has the error correction capability. But still, there is a chance that we are going to make a mistake in our decision. For example, if the channel is too bad, such that we transmit a 1-1-1, but we receive a 0-0-1. So in that case, 2 bits are flipped, and we are going to make a decision in favor of 0, right? So in this case, we see that we have a decoding error, okay? But the majority decision rule, we can prove that it will minimize that kind of error, okay? So that's error correction. And in this class, we are going to focus on linear block code, okay? We are going to focus on linear block code, which is also a very widely used practical coding scheme. So for the linear block code, and every k bits of information corresponds to a code word of length n bits. So we have k bits of information, and we map it to a code word of length n, where n is always greater than k. Okay, n is always greater than k. And as a simple example, in the previous example for the 3 times repetition code, our k is 1 and our n is 3. So 1 bit of information is mapped to a 3-bit code word. Okay, so in general, we have k bits of information mapped to a code word of length n bits. Okay, so since n is always greater than k, so there are n minus k bits of redundancy. So instead of transmitting k bits, we are transmitting n bits. So we added a redundancy of n minus k bits. And the code is called an nk linear block code. Okay, nk linear block code. And as I said, the linear block code is actually widely used as a very simple example for the digital TV that you have at home, and you got the signals from the TV stations, and those signals are encoded by using linear block code. Okay, and we also have a definition of the quantity, which is called code rate, R. R is defined as k divided by n. And this is called code rate. As you can see here, the code rate is always less than 1. Okay, it's always less than 1. And the smaller the code rate means the more redundancy that we have. And we would like the code rate to be as close to 1 as possible, which means we will have as less redundancy as possible in terms of spectral efficiency, right? But inevitably, to get a better protection, we might need to have a lower code rate, okay? And the code rate measures the efficiency of the code, and 1 minus R is the percentage of the redundancy, okay? And for example, for the 3-1 repetition code, R equals to 1 over 3, and in this case, the redundancy is 2 over 3, okay? So it's 66.7%. And for the 2-1 repetition code, the rate is a half, and the redundancy is a half. So we have 50% of redundancy. So the linear block code, it can simply be considered as a mapper, right? So for any k bits of information input, we will have n bits of code word at output. Okay, it's a block, so that's why it's called a block. We have k bits of information block, and at the output we have n bits of information block, and there should be a one-to-one unique mapping between the k bits at the input and the n bits at the output, which means from the n bits at the output, we should be able to uniquely determine the k bits at the input and vice versa. Okay? And it's because of this unique mapping that we can do encoding and decoding. So the problem of channel coding boils down to the question, how do we do the mapping from the k bits to the n bits? So the easiest way of doing the linear block code is just to use a single parity check. Okay? So for single parity check, we add a single parity bit to a block of bits. So in this case, if we have k bits of information, we add 1 bit of parity, so the code word length is k plus 1 equals to n. Right? So in this case, the code rate is pretty high. It's k divided by k plus 1. And we can do either odd parity or even parity. So for odd parity, we add a parity bit such that the summation of all the bits yields an odd result. Okay? Which means there will always be an odd number of ones. Let's see, for example, the first bit is a parity bit, and the remaining bits are the information bits. So in this example, k equals to 1, 2, 3, 4, 5. K equals to 5, and n equals to 6. So in this case, in the original information, we have 2 ones. So to make it an odd parity, we add another 1 such that we have odd number of ones in the end. Okay? So in this example, for the information, we have 3 ones already, which are odd number. So we add a 0 in the parity. Okay? So the parity is good enough for error detection. Okay? So if we are using an odd parity, at the end, at the receiver, we find out we have even number of ones, which means something is wrong, right? We detected an error. For even parity, it's just the opposite. We add the parity bit such that we have even number of ones. And in this example here, the information has 2 ones, so we add a 0, such that the total number of ones is even. Okay, and here we have 3 ones, so we add a 1 here, such that in the end we have 4 ones. So this is even parity or odd parity. Okay, so it can do error detection only, obviously. Okay? If something happens, there is no way for us to identify which bit is in error. So here I have the question for you guys. Will the code be able to detect even number of errors? If 2 bits are in error, doesn't matter it's 0 or 1. If we flip 2 bits, will it change the parity? Think about it. Yes or no? You can exhaustively list actually all the possibilities. There are only 4 possibilities, right? If the 2 bits are 0, 0, they are flipped to 1, 1, will that affect the parity? No, we still have even or odd number of ones, right? If it's 1, 1 flipped to 0, 0, it's not going to affect the parity, right? If it's a 0, 1, it's flipped into 1, 0, it's still the same number of ones, right? And the same thing goes for 1, 0. So if 2 bits are in error and it cannot be able to detect those errors, so which means we can generalize this to even number of errors. Right? So for the parity check, actually it can only detect an odd number of errors. If there are odd number of errors, it's guaranteed that it will be able to detect. It doesn't matter how many bits are in error, as long as it's an odd number of error. If it's an even number of error bits, then it's out of luck. So which means the parity check can detect, the single parity check can detect about 50% of the errors, right? About 50% of the errors. So you can see no error detection or correction is perfect, all right? And there's no such code that it is guaranteed that it will detect any type of error or correct any type of error. Every code, it has its own limitation, its capability, its error correction capability, and its error detection capability. That's why we needed to have multiple layers of error control, right? So at the lower layer, we use a sophisticated code to do error detection, but error correction, even doing that, but still we might have missed some of the error bits, right? And then on top of that, we have another layer of error detection. And then on top, actually at the higher layer, at the transport layer, we also have error controls. So in the communication system, we have several layers of error controls such that to make sure that we can catch all the possible errors. Okay? So in that case, with the several layers, the chance that the final packet that we will receive is in error is very, very small. Okay? So another interesting code is called a product code. And a product code is actually a combination of the single parity bit. So for single parity bit, we just, for a message, we add a single parity, okay? And for the product code or the rectangular code, we actually form a rectangle of message bits of m rows and n columns. And in this example, we have m equals to 3 and n equals to 5, and you can use different numbers. So basically, in this case, the value of our k is m by n, okay? M by n, so in this case, is 3 by 5 is 15. So our information length is 15 bits in this case, okay? Or in general, m by n. So the reason that we want to form it as a rectangle is that for each row, we can add a parity, okay? And in this example, we are doing even parity, okay? So for each row, we add a parity. So here we have 3 ones, so we add another one such that it becomes 4 ones, okay? And we add an even parity here. And each column, we also add an even parity, okay? So here we have a single one, we add another one such that it's even, okay? So even number of ones. Each row each column we have even number of ones, okay? And also in this corner, it's also an even parity. Actually, we can prove it doesn't matter if you do column parity or row parity, this number will always be the same, okay? Because the row and the column, they are calculated from the same information, okay? So this one is actually to make sure that the total number of ones is an even number, okay? And actually we can check 2, 4, 7. So we have 7 ones here, so we need to add another one, make it an 8 one, okay? Or for the row parities, we have 2 ones, and for the column parities, we also have 2 ones, okay? So anyway, so in this case, we have the information length is m by 1, and the code word length is m plus 1 times n plus 1. Okay? So in this particular example, we have 24, 4 by 6, 24 bits in the code word. Okay? So our value of small n is 24, and our value of small k is 15. Okay? So the code rate is capital M, capital N by capital M plus 1, capital N plus 1. Okay? So in this case, any single bit of error, it will flip the parity here, right? So it will violate the parity in its row, and also it will violate its parity in its column. Okay? So in this case, we can find out, for example, if this bit is in error, we find this parity is wrong, and this parity is wrong. So in this case, we can pinpoint which bit is wrong. Right? We find the first row and the second column, the parity is wrong. So we can pinpoint that something is wrong here. Okay? So we can correct this bit. So the product code can actually detect any one bit of error. If there's any one bit of error, we can always correct it. Actually, that's a typo here. It should be correct instead of detect. Okay? So you now see by using a simple structure, adding a simple more structure compared to the original parity code, we can not only detect the error, but we can also correct the error. Okay? We can also correct the error. Any question? All right. So it can detect any one bit of error, and it can actually do more than that. For example, if we have 2 bits of error on the same row, and that will flip the corresponding columns and the corresponding row, we can also correct that. Right? But if we have the errors, 2 errors on different rows, different columns, then it will be more complicated. Right? But anyway, you get the idea. So the rectangular code or the product code can do much, much better compared to the original parity check, okay? We just use a little bit of structure here. And actually the rectangular code can give us a pretty good performance. So to identify which parity bit is in error and pinpoint the location of the bit is one way of decoding, and there are all actually more complicated decoding method, which is called message passing. And that message passing is exactly the decoding method used for the LDPC code. By far, LDPC code is the best code that we know, right? So by using message passing, actually we can achieve a much better performance. But I'm not gonna go into the details here. So that's rectangular code.
I have a question.
Yes.
What happens if one of the parity bits is in error, but the message is correct?
Yeah, for this one, actually we can detect that. So if one of the parity is in error, so all these parities here will be correct, and only this one will be wrong. So we can still identify it's this parity bit, right? So we can still find that out. Good question. Any other question? All right, so before we look into the details of the operation of a linear block code, let's first look at the trade-off that is introduced by the linear block code, okay? So the first trade-off, we can look at the trade-off introduced by the channel coding from different perspectives, okay? As I mentioned earlier, for engineers, pretty much everything is a trade-off. Okay, and for the job of an engineer is actually to find the best trade-off for the job. Okay, so we have a design objective, and we want to find the optimum trade-off that can achieve this objective. And the same thing goes for channel coding. So for channel coding, what we want to achieve is we want to minimize the error probability. By minimizing the error probability, the approach that we use to minimize the error probability is to add redundancy. If we add redundancy, we are wasting the bandwidth resources, right? So instead of transmitting, for example, 100 bits, we are transmitting 200 bits. So there are lots of redundancy in the channel, which means we do not utilize the channel as efficiently as a system that does not have a channel coding, right? So that's a trade-off there. And we can look at this trade-off from different perspectives, okay? So the first way of looking at this trade-off is the error performance versus bandwidth, okay? Is error performance versus bandwidth. Okay, so let's see if we fix the signal to noise ratio and the data rate. Okay, if we fix the signal to noise ratio and the data rate. So in this case, if we are using error correction code, we will have a smaller bit error rate. We will have a smaller bit error rate because the error correction code will correct some of the errors. Okay, our BER will reduce. But in the meantime, the error correction code, because we fix the data rate. Okay, let's see if our data rate is 1 megabit per second. This data rate means the rate of the pure information. The rate of the pure information. So if we use, for example, a code with code rate 1/2, so which means instead of transmitting 1 megabit of information in 1 second, we actually need to transmit 2 megabit of information per second to achieve the same data rate as an uncoded system, because we need to double the amount of information to be transmitted in a unit time in order to keep up with the data rate. So the data rate of the information remain unchanged, but the actual data rate that is in the channel is doubled because of the channel code, right? So here, be careful, we have two different types of data rate here. One is the rate of the pure information, and one is the rate of the actual data that is transmitted in the channel, okay? So by fixing data rate, we mean we fix the rate of the pure information, okay? We transmit 1 megabit of information per second if we use a channel code with rate 1/2, which means in reality, we will need to transmit 2 megabits of data in the channel, okay? So in this case, our actual transmission rate is doubled, which means our bandwidth is doubled, right? As we have learned, the bandwidth is proportional to the symbol rate, okay? If we fix the modulation scheme, our symbol rate is doubled, then our bandwidth is doubled. Okay, so more bandwidth will be required to transmit the combination of the information bit and the redundancy bit. Okay, so to better understand this scheme, and let's look at this graph here. Okay, let's look at this graph here. Actually, we can write the relationship between signal to noise ratio and spectral efficiency. So the signal to noise ratio is essentially, so in the, and actually I use, so let's see PR. The signal to noise ratio only matters at the receiver. So I'm using the power at the receiver to denote the signal power. Okay, so that's the power at the receiver divided by the noise variance. So this is our signal to noise ratio. Okay, so this is our signal to noise ratio. The signal power at the receiver divided by the noise power. So this is the power spectral density of the noise, and that's the bandwidth. Okay, that's the bandwidth. So we talked about this. So the signal power at the receiver is equivalent to EB times RB and not times B. Right? The signal power at the receiver is the energy per bit divided by the duration per bit, energy divided by time. Okay, the inverse of the duration per bit is the rate of the data. Okay, the rate of the data. So that's S on R. S on R equals to EB over N naught times RB divided by B. Right? So this is exactly our spectral efficiency here. Our spectral efficiency. Any question? Okay, so in this particular trade-off scheme, we fix the S on R. Okay. We fix the S on R, and we fix the RB. So this part are fixed. Okay, so this RB again is the data rate of the pure information. We do not consider the redundancy in this case. Okay, and that's how we calculate the spectral efficiency. We only care about for a unit bandwidth how much useful information are delivered. Okay, we don't care about the redundancy. So in this case, our bandwidth based on our analysis becomes bigger, right? Our bandwidth become bigger because of the added redundancy, we need to increase the B to support. We need to increase the B to support the information and the redundancy bit. And in order to, and this N naught is always unchanged, right? It depends only on our device, our amplifier, and the temperature. This is a constant. So here, we have 5 parameters, and 3 of them remains constant, and we need to increase our bandwidth to support more redundancy bits, which means equivalently our energy per bit also increased, right? In order for this equality to hold, okay? So this EB means equivalently we are allocating more energy for each bit, which is not difficult to understand. So previously, we are just transmitting 1 bit of information with uncoded system. Now, for example, if we have code rate of 1 over 2, which means we are using 2 bits to deliver the information of 1 bit, right? So the total information for the total energy for 1 information bit is actually the combined energy of the information bit and the redundancy bits. So equivalently, we are giving more energy to each information bit. Right? We are giving more energy to each information bit because we also need to allocate energy to the redundancy. Okay? And those energy eventually will be calculated according to how many bits of information that we calculate. So this EB is essentially the total energy divided by the total number of information bits. Okay? So that's the EB here. The total energy divided by the total number of information bits. Because we are transmitting redundancies, so the total energy will be bigger, right? And the total information bits remain unchanged. Therefore, equivalently, we are allocating more energy to each information bit. And which means the EB0 and not becomes bigger. Okay? The EB0 and not becomes bigger. And because if we look at the beta error rate curve and the EB0 and not becomes bigger, so equivalently, we are going to get a better error probability. Okay? So that's the first trade-off. If we look at the trade-off between the error performance and the bandwidth, so basically we are gaining error performance by sacrificing the bandwidth. Right? So that's the first way of looking at that. If we fix the signal-to-noise ratio and the data rate. So in the next trade-off is the power and the bandwidth. Okay, the power and the bandwidth. So basically, in this case, if we fix the beta error rate and the data rate. Okay, if we fix the beta error rate and the data rate. So in this case, if we fix the beta error rate and the data rate, the error correction code will require a smaller EB0 naught, right? Because of the actual redundancy, we only need a smaller EB0 naught to achieve the same performance. Therefore, we will require. So if again we look at this equation, still those parameters. So here we have EB0 naught and a PR and R. So N naught is always a constant. Okay, it's always a constant, and we also fixed the R. Okay, we fixed the R. So in that case, if we are using error correction code, for example, let's look at this point here. So without channel code, we need to operate at point B, and with channel code, we can operate at point C. So we will require a smaller EB0 naught. So this EB0 naught becomes smaller. If this EB0 naught becomes smaller, means the PR will also becomes smaller. Okay, so the PR will also become smaller. So in this case, so we can save the power, right? We can save the power. But in the meantime, because we are using error correction code, and more bandwidth will be required to transmit. Okay, so it's a trade-off between power and bandwidth in this case. All right, it's a trade-off between power and bandwidth. So because we reduce EB0 naught, we reduce PR, so we require less power. We reduce PR, we reduce PT. Okay, but in the meantime, because we still have the same data rate, as long as our data rate is unchanged, our bandwidth has to be increased. Right? Our bandwidth has to be increased. So that's the trade-off between power and bandwidth. If we fix the beta error rate, so in the previous trade-off, actually, if we fix the signal-to-noise ratio and data rate, and actually we can use a larger bandwidth and to get a smaller, we can get a smaller error probability, right? So it's this direction here. Okay, we can get us. Previously, our beta error rate is 10 to minus 2, and now it's 10 to minus 4. And in this trade-off, if we fix the BER, it's moving in this direction horizontally. Okay, we move from point B to point C. Okay, so also we can define something that is called coding gain. So at a given beta error rate, the coding gain is the difference in EB0 naught between coded and uncoded system. Okay, so here for the uncoded system, for example, at here for the uncoded system, the required EB0 naught is somewhere around 12 dB, right? And for the coded system, to achieve 10 to minus 4, the EB0 naught is 8 dB. So the coding gain in this case is about 12 minus 8, which is 4 dB. Okay? So the coding gain is defined as the reduction in required EB0 naught to achieve the same beta error rate. Okay? And that's called the coding gain. Any questions? So that's the second type of trade-off. And by using channel coding, we can achieve trade-off between power and bandwidth. Okay? And again, this EB here is the energy per information bit. Okay? We don't count those redundancy bits to ensure a fair comparison. Okay? To ensure a fair comparison. And the third type of trade-off is the trade-off between data rate and bandwidth. So in this case, if we fix the beta error rate and the transmission power, if we fix the transmission power, which means we fix the receiving power, right? So if we fix the BER and the transmission power, so which means now PR is fixed, okay? PR is fixed, and N naught is always fixed, okay? So if we use error correction code, which means we require a smaller EBR N naught. So if we require a smaller EBR N naught, PR is fixed, N naught is fixed, so which means R has to be increased, okay? R has to be increased. So in this case, we have a larger data rate. We have a larger data rate. And again, error correction code, we still need more bandwidth to transmit the information. So in this case, it's a trade-off between data rate and bandwidth. So as we can see, in the design of the system, we can achieve different types of trade-off. Just depends on how you design the system, right? For example, if we want to achieve the trade-off between power and bandwidth, we simply fix the beta error rate and data rate, okay? We want to design a system without changing the data rate and without changing the beta error rate. And by using channel coding, we can reduce the power consumption and increase the bandwidth consumption, okay? And which kind of trade-off that we want to use, it just depends on the specification of the particular system, okay? So by using error correction, and we can achieve different types of trade-off, okay? And for all these trade-offs, essentially, we are gaining performance in one aspect, we are losing performance in another aspect. It just depends on which is more important for our system, okay? There is no free lunch. So gaining something, we have to pay a price. So that's just the basic concept of structured sequence and channel coding. Now it's time for us to move on to the details and look at how linear block code is designed, okay? So the rectangular code is a special case of the linear block code, okay? And in this section, we are going to look at the general rules for designing a linear block code. Okay? And in order to design linear block code, first I would like to introduce the binary operation, okay? The binary operation. So here, we are using O plus O is O plus 1 is 1, 1 plus O is 1, just simple algebra. The only thing that we need to be careful is 1 plus 1 equals to O, because we are only dealing with binary numbers here, okay? There is no 2 in a binary system. So when 1 plus 1 is actually 0, okay? And the multiplication is the same as our regular algebra, okay? O times O times 1, and 1 times 1, okay? So also we will need to use matrix operation, okay? And we will need matrix operation. And for example, if we have two matrices, and matrix A is 3 by 3, and matrix B is 3 by 2, okay? 3 rows and 2 columns. And if we multiply these two matrices, and what we are going to get is a matrix C, which will be 3 rows and 2 columns, okay? And the basic idea of matrix operation is, so for the element on the first row and the first column of C, is obtained by multiplying the first row of A and the first column of B, okay? And for the element on the second row and the first column of C is obtained by using the second row of A and the first column of B, okay? And in general, for the element on the mth row and nth element of C, CMN, is obtained by multiplying the mth row of A and the nth column of B. Okay? Just simple matrix operation. For example, C21 is the second row of A times the first column of B, right? So the second row of A times the first column of B is A21 times B11 plus A22 times B21 times A23 times B31, okay? So that's just simple matrix operations. And if we do the multiplication between two matrices, and the column number of A has to be the same as the row number of B, right? Otherwise, we won't be able to do the row times column operation, okay? So that's called the inner dimension of those two matrices. The column number of A has to be equal to the row number of B. And in this particular example, we have 3 columns for A and we have 3 rows for B, so they can be multiplied together, okay? So the product of an m by k and a k by n matrix will be an m by n matrix. Okay? The inner dimension is k columns in A and k rows in B. So that's just a quick review of basic matrix operation. Okay? So we are going to look at, I'm going to introduce linear block code by using a simple example. And this example is a 7-4 code. And for this 7-4 code, we have 4 bits of information and a 7-bit code word, okay? Which means k equals to 4 and n equals to 7. So in this case, we have a redundancy of 3 bits for each code word, okay? We have 3 bits of redundancy for each code word. And for information vector, because we are using 4 bits of information, so there are 16 possibilities of informations, right? From 0000, 0001, all the way to 1111. Okay, so we have k bits. So totally, each bit has 2 possibilities. We have a total of k bits, so there are a total of 16 possibilities. Okay, so we have 16 possible information vectors, and each information vector will be mapped uniquely to a code word. So which means we also have 16 code words. We have exactly 16 different distinct code words. Okay? And however, the length of our code word is 7 bits. Okay? So if we look at all the possible combinations of 7 bits, we have 2 to the power of 7, which is 128. Okay? There are a total 128 possible combinations of any 7-bit sequence. However, we only need 16 of them. Right? Only 16 of them will be valid code words, and all the remainings will be invalid sequences. Okay? So the code design is a short, for the design of linear block code, essentially boils down to the problem. We have 128 possibilities, and however, we only need 16 out of these 128 possibilities. So the question is, how do we pick the 16 code words out of these 128 possible code sequences? Okay? So the optimum design of the code word is just to find out the best possible combination of these 16 code words such that we can have the minimum error probability. Okay? So that's the core idea of linear block code. Okay? We have those many possibilities, but we only need a subset of them. And how do we pick this subset? Okay? The most straightforward way of doing this is just to do an exhaustive search. So we have 128 candidates, and we only need 16 of them. So we just pick 16 of them, and we try them and see what is the error probability. Okay? And then we pick another 16, and then we try this again. Right? And we can exhaustively list all these possibilities, and based on the combinatorics, there is a total of 128 choose 16, and that's actually an astronomical number. Okay? And in reality, we can't do that. The complexity is too high. Right? But if assume that we have a computer that is fast enough that we can exhaustively list all the possibilities, we will guarantee to find the best code word. Okay? So even for this one, it's possible. Actually, with today's computer, it's still possible. But here it's simply just a 7-4 code. Right? So if you imagine if we have a 128 to 64 code, 128. If we have a 128 64 code, then our possibility will be out of 2 to 128, we need to pick 2 to the power of 64 possibilities. And then this is impossible, right? This is impossible. So obviously we cannot do it in that way. And actually, there are, even though we cannot do the exhaustive search, okay, its complexity is too high, but we can follow the theories from algebra, and we will still be able to find the optimum code. okay, without going through this kind of exhaustive search. Okay, and that's what we're going to study. We are not going to study the actual math that is behind the design of the code. Okay, I'm only going to introduce how we do encoding and decoding. Okay, and it will require actually very advanced math in order to study how to design the different channel code. Okay, and you will need a math degree to do that actually. All right, so for the practical linear block code, so what we do is we are using our information sequence to multiply a matrix. Okay, our information sequence has a length of k, and this matrix is called the generation matrix. Okay, so this generation matrix has a dimension of k by n. Okay, so in this particular case, k is 4 and n is 7. So we have a 1 by 4 information sequence times a 4 by 7 generation matrix, and what we will have in the end will be a 1 by 7 code word sequence. By using this simple multiplication, we can get a code word. Okay, we map a 4 bits information into a 7-bit code word. Okay, into a 7-bit code word. So the design of the coding for the linear block code, it boils down to the design of this matrix here. Okay, and again, as I mentioned, I'm not going to talk about how to design this matrix because it will require very advanced algebra to understand this. Okay, so I'm simply presenting the result. So for us engineers, all that we need to know is these metrics are designed by mathematicians. Okay, and once it's designed, we can utilize that. So as a very simple example, we can find the code word for the different sequences. And oh no, is there any way that I can directly write on here? Anyway, so okay, here. So we have this generation matrix. This generation matrix is a practical generation matrix used in real systems. Okay, so the code word, let's just look at this simple example here. So our generation matrix in this case is and okay, so this is our generation matrix. And given, did I make a mistake somewhere? Oh, okay, yeah, right. Thank you. Yeah, should be 7 columns instead of 8. So given this generation matrix, we can always find the code word x times g. So I use this underscore to represent it's a vector. So if x, for example, is 0, and 0 times anything will still be 0. Okay, so for all 0 sequence, its all code word will be 0. And for the second example, we have 0011 times g. So in this case, so the 0011, so we will have this row times the first column. It will be the result in the first row and the first column, right? And the first row times the second column. So again, it's going to be 0. And the first row times the third column, so we will have a 1 times 1 there, okay? And it's going to be a 1. And the first row times the fourth column, and again we will have a 1 times 1, which is a 1. And the first row times the fifth column, so we will have, again, a 1 times 1 here, that's a 1. And the first row times the sixth column, so we have a 1 times 1 plus a 1 times 1, okay, which is 1 plus 1, it's a 0. And for the final column, we have a 1 times 1, which is here. Okay, and actually there's an easier way to interpret this, because the first two elements are 0, so the first rows will always have give us 0. Okay, only the third row and the fourth row So what we have is actually the third row plus the fourth row. The third row plus the fourth row will be exactly what we have here. Okay, so this code word is the third row plus the fourth row. And in the next example, 0101 times G. So in this case, actually, it's the second row plus the fourth row. Okay, so the second row plus the fourth row, we will have 0101. 1, 0, 0, 1, 1, 1, 0, 0. Yeah, right. So that's correct. So these are the three different code words. Okay, these are the three different code words. Any question? All right. So that's just a simple example of the 7/4 code, and in general, so for the NK linear block code, we have k bits of information and n bit of code word, and the information vector is a 1 by k row vector, and the code word vector is a 1 by n row vector. Okay, and there's a linear relationship between information vector and a code word vector. Okay, so that's why it's called a linear block code, because it's a linear operation. X times G is a linear operation. That's called a linear block code. Okay, so the matrix that I show in the previous slide, if I go back, this is the best possible matrix for a 7/4 linear block code. Okay, and we can prove that by using algebra. But there are always, you can see, possibilities of a nonlinear code, right? And because there are 128 out of 16, choose 16 out of 128 possibilities. If we allow nonlinear relationship, we might be able to get better performances. Okay, but right now all the codes actually that we are dealing with are linear codes, because nonlinear code will be extremely difficult to design. Not only the encoder, but also the decoder the complexity will be too high. So almost all of the channel codes nowadays are linear block code, are linear code. Okay, are linear code. And actually, the most advanced code, as I said, the code that has the best performance, which is a low density parity check code, LDPC code, is also a linear block code. Okay, it's just a linear block code with extremely large size. For that code, the value of n and k are on the order of a few thousands. Okay, on the order of a few thousands. And what makes it the performance better is actually the design of the decoding algorithm and the design of this matrix here. Okay, and you can imagine at that scale and the design of this matrix can be very difficult. Okay, and there are algorithms to design this matrix. So LDPC code is actually a special case of linear block code. It follows exactly the same principles that we are discussing here. Okay. Anyway, so we will have a generation matrix, and for the generation matrix, and this is one way to represent a generation matrix. And for this generation matrix, it can be decomposed into two blocks. The first block is a key by key identity matrix. Okay, for identity matrix, it means it's a diagonal matrix, and with all of its diagonal elements being 1, and everything else are zeros. So that's an identity matrix, and we represent it by using the letter I. And also we have a P matrix. Okay, a P matrix. The P is used to calculate essentially the parities. Okay, the parities. So if the generation matrix satisfies this particular structure, if the generation matrix follows this particular structure, so we will have X times I times I and P, okay? So if we do matrix multiplication, and our code word will be X times I and X times P, okay? And any matrix times the identity matrix will be itself, and then we will have X times P here. So which means for the code word, the first k bits will be exactly the same as our original information. And the remaining n minus k bits are actually the parities of those first k bits. Okay? Instead of using one parity, we use a sequence of parities, n minus k parities. Okay? And if we look at this example, this is always true. So for C, the first code word, the information is 000, and the first 4 bits are 000, which is exactly the same as our information bits. Okay? And for the second example, we have 0011 here. And for the third example, we have 0101 here. Okay? And the remaining 3 bits are obtained by using a linear combination of these first 4 bits. Right? That's why they are called parity. They are linear combinations of these first 4 bits. And if you check this matrix, and actually, you can see the first 4 columns, they form a 4x4 identity matrix, and then the remaining 3 columns are used for parity calculation. Okay? So this type of code is called a systematic code. This type of code is called systematic code. So by systematic code, we mean the first k bits of the code words are exactly the same as the information bit. Okay? If this condition is satisfied, it's called a systematic code. Okay? Again, the first k bits of the code word are exactly the same as the original information bits. This is called a systematic code. And of course, you can imagine we can write different forms of G without following this structure. We can have non-systematic code. Okay? We can have non-systematic code. But it has been proved that for any non-systematic code, it can always be equivalently converted into a systematic code, which means the non-systematic code cannot perform better than its equivalent systematic code. So there is no point for us just to design a non-systematic code because it's not going to give us a better performance. So which means for any non-systematic code, we can always find a systematic code that has exactly the same performance. Okay, so that's the equivalence between non-systematic code and systematic code. And for this reason, most of the practical codes used in the world are systematic code. Okay, because it's easier in this case. We see the code word, we will know what are the information. Okay, and you can design the different metrics to be non-systematic, but we can always find a systematic code that has the same performance, which means we only need to design systematic code. Okay, so this is called the systematic code. Any question? All right, so that's the generation matrix. Okay, and the performance in this case, the operation of the encoder is just the multiplication of the information vector with the generation matrix. Okay, so for the generation matrix, we can write it in this way. So G1 is the first row of the G matrix. G2 is the second row of the G matrix. So totally we have k rows. And if we multiply this row with this vector here, it can be compactly written as x1 times G1 plus x2 times G2 and all the way to xk times gk. Okay, and each one of these here is a row, so we are actually adding up the k rows. Okay, and we give each of this row a weight. Okay, that's exactly what I did in the previous example, right? If the first 2 bits are 0, then I don't need to worry about the first 2 rows, right? I only need to add up those rows with x corresponding to 1, and that's it. Okay, that's exactly what I did in the example. So for this example here, the code word for 0100 will simply be the second row. Okay, and the code word for 0101 will be simply the summation of the second row and the fourth row here. Okay, so in this case, we can find the code word for all those information sequences. And also for this reason, each row in this generation matrix is a code word, right? Because if we have a 1 here, so the second row is a code word, right? If we have a 1000, then the first row will be a code word, right? And every single row of this generation matrix is a valid code word, all right? Question? All right. And actually the combination of this code word, so totally we have 2 to the power of k sequences. We have 2 to the power of k code words, okay? And the combination of these 2 to the k code word in mathematics is called a field, okay? So for a field, it means for any linear combinations of 2 elements in the field is still in the field, right? And also it has a 0 element in the field. So if our information sequence is all 0, then the code word will be 0, okay? So 0 is an element of a field. And another requirement for the field is any linear combination of the 2 elements. So each row can be considered, each code word can be considered as an element of the field, right? Any combination of two elements in the field, it's still in the field, okay? So it's closed. So just now we introduced the generation matrix, and also there is another matrix which is called a parity check matrix. So the parity check matrix usually we represent it by using the matrix H, and H has a dimension of n rows and n minus k columns, okay? So in the, if we recall, so for G, we have ik and p, k rows, n minus k columns, okay? And we can shuffle this matrix and manipulate the locations, and we can have a parity check matrix is we put k on top, and we put p on top, and on the bottom we have an identity matrix that is of size n minus k. So if you look at this matrix, its size is n by n minus k. So this is called the parity check matrix. So this basically, given the generation matrix, we can always get the parity check matrix, and vice versa, right? Once we have the parity check matrix, we can always find the generation matrix. So which means there is a one-to-one mapping between these 2 matrices. So why do we need a parity check matrix? And the reason is we have a very nice property of these 2 matrices. Let's see if we have G times H. Okay, if we have G times H. So if we write them in the form of block matrices, ik, p, k, n minus k times H, p, k by n minus k, I, n minus k. Okay, let's multiply these 2 matrices. And based on the rule of block matrix operations, we can just treat each block as an element. Okay, so we have a row times a column. So in this case, it's ik times p, k by n minus k, plus p, k by n minus k times I of n minus k. Okay? So if you look at the matrix operations, their inner dimensions always match, right? So this one has k columns, this one has k rows. And this one has n minus k columns, and this one has n minus k rows. Okay? So anything multiplies an identity matrix will be the self. So this will be pk by n minus k, and plus p k by n minus k. So we have the summation of these 2 P matrices, and they are exactly the same. Okay? So it's tempting to put it as here, but in binary operations, we don't write it in that way, because we always have 0 plus 0 equals to 0, and 1 plus 1 is also gonna be 0. Okay? So they have exactly the same elements on their respective locations, so we always have 0 plus 0 and 1 plus 1. Which is 0. So G times H is always 0. Okay? G times H is always 0. So that's actually a very useful property. And why is this useful? This property can actually help us to identify which bits are in error. Okay? And the reason for this is our code word is simply a linear combination between x and g multiplication. So which means if we multiply C with our parity check matrix, we will have x times g times h, right? C is exactly x times g. And its multiplication, it doesn't matter what is the order of the multiplication. So this will always be 0. Okay? So if it's a valid code word, we multiply it with h, we will always get 0. Okay? So this can be used to check if what we received is a valid code word. If what we received is not a valid code word, it multiplies h, it will be non-zero. Okay? So that's why it's called a parity check matrix. This matrix is used to check whether there is error in the received information. Okay? So that's called a parity check matrix. You can see it's a very simple scheme. Okay? We simply just do a matrix multiplication. That's it. Okay? And we are going to get the desired result. Any question? And just now I mentioned that the low density parity check LDPC code. Okay? So far the best code, as I said, is LDPC, and it has been incorporated in the standard for the 5th generation wireless communication system, which you're going to start to see them probably towards 2019 and 2020. Okay? At that time, we are going to see 5G systems started to be deployed, and this is called low density parity check, okay, LDPC. So if you look at the name, actually it's defined based on this parity check matrix, okay? And the low density here means for this particular parity check matrix, there are a lot of zeros compared to the number of ones, okay? So the basic idea is on each row of this parity check matrix, we will only have a few ones. And if you look at every column, we will also just have a few ones. Okay? So let's see if the size of the matrix is a very commonly used number, for example, is the code word length is 5,192. Okay? So for a code word that long, if you check every row and every column, there might be just 2 or 3 ones. Okay? The majority of them are going to be zeros. That's what low density means. Okay, and it's a linear block code. And given that H matrix, but now this H matrix is not necessarily a systematic code. So which means this H matrix not necessarily satisfy this structure here if it's not a systematic code. Okay, so the design of the H matrix actually is just to find out in which rows and which columns we should put the ones there. Okay, and we only have just a few ones. Okay, so once we figure that out, we have the H, and given the H, we can find out what is the generation matrix. Okay, and but once we have the generation matrix, the encoding is very simple. Just do x times g, and that's it. Okay, we have the code word, and then but for the decoding, we can use the code word to times h, but this will only tell us if there's error or not. It can only detect error, it cannot correct error. Okay, so in order to correct error, we use something called message passing, and which I'm not going to go into details in this class. If you are interested, you can look up online, and for graduate students, you usually have no trouble understanding the operation of message passing. It's an iterative algorithm, and for decoding, basically we use the H matrix. We use the structure of the H matrix, and we are essentially doing an iterative decoding procedure, and eventually we can get a performance that is very, very close to the channel limit. Okay, so that's the best code that we have so far. Any questions? So that's just a special case of linear block code. Okay, it's quite surprising that in the end the best code is actually a linear block code. Okay, and linear block code was the first type of code that was developed. Okay, and half a century ago, and it has been used in many communication systems and people feel that its performance is not that good, so they started to study more advanced coding schemes like convolutional code, right? And the convolutional code is introduced in the class of wireless communications and also turbo code. And eventually people found out that the linear block code can, as long as we design it with a special structure, we can achieve very good performance. Okay, and the LDPC was first introduced actually also in the 1950s, 60s, as I mentioned earlier, by Professor Gallagher from MIT. But at that time, he introduced the concept of LDPC. He said, we can design edge with very small number of ones, and we can achieve very good performance. And he proved that by math, in theory. But he doesn't know how to actually design this code, and especially the decoder. Okay, so at that time, so half a century has passed, and that code has been forgotten until the late 1990s, and that was after the introduction of turbo code. And for turbo code, people are using iterative decoding, and they found out that by using iterative decoding, they can achieve very good performance. And then people go back to the textbook written by Professor Gallagher and look at this LDPC code, and then suddenly they realized that we can use iterative decoding to do for this one as well. So they tried that, and its performance is really, really good. Okay, and then there are tons of papers talking about why the iterative decoding will work for this one. Okay, it was published mainly during the early 2000s. Anyway, so that's just another story of linear block code. So this is the parity check matrix. Okay, so for linear block code, it's uniquely defined by a generation matrix or a parity check matrix. Given any one of these two matrices, we will be able to find another one, and then we can perform encoding. Okay, so in general, the encoding procedure is simple. Okay, for most of the code, it doesn't matter it's turbo code or linear block code or convolutional code or LDPC code. The encoding is simple, and what is complicated is actually the decoding procedure. Okay, and there are many different ways to do decoding for linear block code. And in this class, we are just going to look at a simple one, which is called the syndrome decoding. Okay, and the syndrome decoding is again associated with the parity check matrix. Okay, so let's see. We have a code word, and we transmitted this code word, and because of the errors in the channel, some of the bits are flipped, and this is what we received. Okay, so this error vector is still just ones and zeros. Okay, if there is a 1 in the corresponding bits, which means what the corresponding bit is flipped, there is an error there, right? So we have an error vector. So this is what we received. So once we receive this vector, what we do is we perform R times the parity check matrix. So this will give us C plus E times the parity check matrix. Okay? So if we write it out, we will have C times H plus E times H. And for C times H, as we have learned, it's always 0, because C is a valid code word. So what is remaining is E times H. So this R times H is in general non-zero. And the non-zero elements is contributed by the error vector here. Okay, and we call this as the syndrome. Okay, so the syndrome is a direct consequence of the error vector. Okay, syndrome. Just like if you go to a doctor, let's say you have runny nose, that's your syndrome, and the doctor will deduce that probably you got a cold, right? That's the syndrome code. So your running nose is a direct consequence of you catch a cold, right? So this S is a direct consequence of E. So S is a syndrome of E. So what the doctor is interested in is to find out what is your sickness, right? And what we are interested in here is what is the error vector by looking at the syndrome. Okay, so in general, if there is a unique mapping between S and E, and then there is no problem at all, right? So given looking at S, let's see if the running nose can only be caused by catching a cold, then it's really simple to be a doctor, right? You have a running nose, then you have cold, then I prescribe some cold medicine and that's it, okay? And so that's the same thing. If there is a unique mapping between S and E, we look at the S, we know immediately what is E, and if we know E, and just keep in mind, everything is binary, so R equals to C plus E. If we know what is E, we just do, and the E is binary, E plus E is again just 0. We recover the original code word. Once we find C, the first k bits will be our information, and that's it, okay? Unfortunately, we are living in a real world, and nothing is that simple, right? So the problem here is the syndrome and the error vector, there is no one-to-one mapping. Just like you have a running nose, it might be caused by something else. So different error vectors might cause the same syndrome, okay? So that's what makes things complicated. Anyway, so I'm going to stop here today, and we are going to continue next week to talk about syndrome decoding, right?
Still finish with the project, so when I can have this.
All right.